A simple example of application of Noether's theorem is in the case of massless scalar fields. So that's just the Klein-Gordon Lagrangian with no mass. And this Lagrangian has a lot of symmetries. And one obvious symmetry is if I change the amplitude of the field by a constant everywhere, that doesn't change my Lagrangian, therefore that has to be a symmetry. We define Noether's theorem using infinitesimal transformation, even though it's not necessary here to take them to be infinitesimal. But just to recognize the different quantities we introduced, let's write. Of course, here delta S phi is just 1. And for the Lagrangian, we see that delta SL is 0. And for this to be a symmetry, this must be equal to the covariant derivative of the function f. And because this is 0, we can simply take f to be equal to 0. And we can now write Noether's current. So this is 1, this is 0, and this we can easily calculate from the expression of the Lagrangian. So let's verify that this is indeed a conserved current. And because our field is a classical field, it must obey the classical equation of motion, which in this case is the Klein-Gordon equation with no mass, so therefore del squared phi has to be 0. So Noether's current for this transformation is indeed conserved in the sense that del mu j mu is equal to 0. And if we want to find the conserved charge associated with this symmetry, we just integrate over space the time-like component of Noether's current.